Hello, this is Ezra back with AP Calculus A, B, and BC review. This is Unit 2 Derivatives, where we cover the limit definition of the derivative, different techniques for differentiation, special derivatives, which can't be derived from the normal techniques, and we cover differentiability and mean value theorem. So let's get started. Now, what is a derivative defined as? Well, I'm going to draw a function with points A and points B. And if you wanted to draw the average rate of change between them, which would be the slope, it would look something like that. And you would find it by f of B minus f of A over B minus A. Now, what if, for instance, you wanted to find the slope at point A? Well, to do that, you would make the distance between point A and point B smaller and smaller. So, what you can do here is, let's say you place point B here. This average rate of change is looking more and more, I'll use a different color, is looking more and more like the average rate of change at A. So, how we can write this is the average rate of change between 2 points is just f of x, whatever point it is, plus delta x, or we're going to use h equals delta x to make it look a little nicer. So we're going to say f of x plus h minus f of x, which makes sense because we're taking the point of f of x, whatever number it is, and then we're adding the change in x between that point and the new point. And then you just divide it by the change in x. So this right here is the change in y, because it's y2 minus y1. And then the bottom is just a change in x. So what we do with this is we put a limit onto it. Limit as h approaches 0 of f of x plus h minus f of x over h. So, as h, which is the change in x between the 2 points, goes towards 0, this is just our average rate of change function at that point, at the original point, because the change in h will eventually be 0. But if you look at this, we're going to have a 0 on the bottom. So that looks like it's going to be a problem. But I'll show you why it ends up working out. So I'm going to get rid of this stuff up here. And I'm just going to take this definition, and let's take the function x squared. Let's say I wanted to find the slope at x equals 1 of x squared. So this function, I just drew a random arbitrary function here, but for x squared, I want to find the slope right here. So what is this slope at x equals 1? Well, first I should plug in x squared. So f of x plus h of x squared would be x plus h squared. You're plugging this into x squared. So, if you wanted to find what the slope was, you could say, okay, what is x squared at x equals 1? Well, it's just going to be 1. So, the slope at x equals 1 would be limit as h approaches 0 of f of 1 plus h squared minus f of 1 over h. Let's see what happens here. F of 1 plus h squared. Or actually, it's not going to be f of 1 plus h squared. It's just going to be 1 plus h squared. Because that is what we plugged in over here. Now we're going to have 1 squared plus 2h plus h squared. Alright. Minus f of 1, which we said is 1, over h. And the limit, remember, you can't forget this limit, is still approaching 0. So this one cross out. 1 minus 1 crosses out. And now, we're left with 2h plus h squared over h as the limit of h approaches 0. So, what you can see here is that these h's will mostly cross out. This h crosses this h, and this same h crosses the exponent off of this one. So you're left with 2 plus h. So, if we take this limit as h approaches 0, plug 0 into here, we find out that the slope of x squared at x equals 1 is 2. Now that might have looked like a lot, because it was, but you do not have to do that whole process for every single number. Because if you think about it conceptually, what if we just plug x in as our number? X can be the point. So we can then, once we plug x plus h and then x into our definition over here, we'll get a general form where we just plug the x number in and then we get the slope at that point. So, let's try that here. F of x plus h is x plus h squared. So x plus h squared, which I'm just going to simplify it right now. You can FOIL it out. X squared plus 2xh plus h squared. Minus f of x, so we're just going to minus the x squared, over h. Now, x squared and x squared cancel out. So you're left with the limit as h approaches 0 of 2xh plus h squared over h. Again now, every term has an h. Cross out h's, h's, h's. Then you get 2x plus h. This limit, as h approaches 0, well, plug the 0 in, you end up with 2x. So this is our derivative of x squared. This will find the slope at any point, given the x value. And we had to do all this work to do it. Now, there is a simpler way. Because if you had to do all this work every time, that would be ridiculous. So, pretend this is still our x squared function. The power rule will help us find the derivative of this x squared. So we're going to denote that as f prime of x. That's the derivative. And now the power rule states that if you have any function x to the n, the derivative will be nx to the n minus 1, which here you have x squared. Transform that. 2x to the 2 minus 1 equals 2x, which that took about 3 seconds, and that gives us the same answer as before. That is the correct answer. So, this can be done with any normal polynomial. So, let's say you have some crazy function x to the 4th minus 3x cubed plus 7x minus 1, right? You can just do the power rule. And I'm going to individually do it up here. 4x to the 4 minus 1 minus 3 times 3x or I'll just write the 3. 3 times, you already have the 3x to the 3 minus 1, plus 7 times 1, x to the 1 minus 1, and then careful here, this negative 1. What do you do with this negative 1? So, negative 1 times 0 to the x to the 0 minus 1. Now, since this has a 0 in it, this part, it doesn't matter. This whole thing cancels out. So, that's another rule. The derivative of any constant number will just be 0. So now, we take this, and now we multiply, add them together. 4x to the 4 minus 1 is 4x cubed. 3, and then we already have a 3x to the 3 minus 1. That gives us 9x squared. 7 times 1 to the x to the 1 minus 1. X to the 1 minus 1 is x to the 0, which is 1, plus 7. And negative 1, we've already established that becomes 0 because it's a constant. So this is our derivative. So it doesn't matter how many terms you have, as long as it's a normal polynomial, you will be able to take the derivative of it. Now, what happens if you have something a lot longer? Let's say you have x minus 7 x squared plus 4. If you wanted to take the derivative, or I should say x plus 4. Now, one way you could do it is by foiling this out and then doing the power rule. But that takes too long. So, an easier way to look at it is with another rule, the product rule. Let's say you have any function u times v, right? These will just represent functions. If you want the derivative of it, we'll denote d over dx. Then you have the derivative of u, which we'll put u prime, times v, plus u times the derivative of v. So what will that look like here? Well, the derivative of x minus 7, we can just put these as two separate terms that are multiplied. So the derivative of x minus 7, right? Well, the derivative of minus 7 is nothing. And the derivative of x is 1x to the 1 minus 1, which is just 1. So we can say the derivative of x minus 7 is just 1. And then we times it by our other function. So 1 times x plus 4 plus the derivative of this function, which again, the plus 4 is nothing. And then the x just becomes 1. So we have 1 and then x minus 7. And then if you wanted to simplify, you could. X plus 4 plus x minus 7 equals 2x minus 3. And that's your answer. And again, this works for any function. Any function. You can have some crazy x cubed minus 7x squared plus 4x times 2x minus 1, or it will work for even special functions, which we'll talk about later in the video. But this rule right here is very important to know. The next rule is the quotient rule. So, let's say you have x squared plus 4x minus 3 over 7x. Now, you could split it up, divide it, however you want. I'll get rid of the 3, in fact. If you wanted to, you could split this up and divide it. However, the quotient rule here would probably be easier. So what is the quotient rule? Well, it is, if you have a function, u over v, d over dx. And I'm going to move this down here just to be cleaner. It will be the derivative of u times v minus, this is very important, minus u times the derivative of v over v squared. So there's many different, expressions that you can use to memorize it. I like low d high minus high d low over low low. But whichever way you want to memorize it is up to you. So here, we're going to do that for this function. Now we have 7x times the derivative of the top. So we have 7x, and then the derivative of x squared plus 4x. With the power rule is going to be 2x plus 4 minus the top times the derivative of the bottom. Derivative of 7x is 7, and then the top is x squared plus 4x over 7x squared. So 7x squared. This would be a valid, complete answer. If you wanted, you could turn this bottom part into 49x squared, which you might see on the AP test, on a multiple choice answer. Or they could distribute. But either way, it will be the same thing. And that is how you use the quotient rule. So, finally, we have the chain rule, which is probably the most important one other than the power rule. So, if you have a function inside of a function, how would you solve this? So, what does a function inside of a function even look like? Well, you could say x squared minus 4 cubed. So now, this is essentially like saying you have x cubed, and you're putting x squared minus 4 inside of the x cubed. So what would this look like? Well, you have derivative outside times the inside function times derivative of the inside function. So that seems a little unintuitive, but all it's saying is you treat this as a variable for the outside function. So this outside function is x cubed. So you have 3 times x squared minus 4 squared. That's this part. All we did is we did the power rule. We brought the 3 down, minus 1. And now we have to times it by the inside function, which is x squared minus 4. We know the derivative of x squared is 2x, and the derivative of a constant is 0, so g prime of x, which is our inside function here, is just 2x. And this is a final complete answer. And there are endless examples of the chain rule. I'm going to give another one, and it's going to be a little bit harder. I give x cubed minus 2x to the 3 over 2. You can take a second if you want to do that yourself before I work it out. Okay, now we are going to have 3 over 2 x cubed minus 2x to the 1 over 2, because 3 over 2 minus 1 is 1 over 2, times, you need to put parentheses, 3x squared minus 2. this is our final answer. It's pretty intuitive once you get the hang of it. And it is weird at first, but eventually it just becomes natural. Now we're going to go over some special cases of derivatives. So I have 9 here, but they're kind of grouped into 3 separate categories. So we have a to the x, e to the x, log base b of x, ln of x, and then the 6 trig functions. But really, you only need to know 2 to be able to figure out the rest. So let's start off with our a to the x and e to the x. What would that even look like as a derivative? Well, a to the x, the derivative of it is just the natural log of a times a to the x. It's as simple as that. You just times it by the base. And then, as you can imagine, e to the x is ln of e times e to the x. But because ln of e is just 1, the derivative of e to the x is e to the x. And for these functions, the chain rule can be applied, as well as product, as well as quotient, as well as not power, but the other 3 can be. So, if we have e to the x squared, take a second, think about what that would be. Think about what the inside sort of function is and what the outside function is. So, this is the function e to the x, with x squared being the inside function. So, the derivative of this is the outside function, which e to the x doesn't change. So we just have e to the x squared, timesing it by the derivative of the quote inner function. It doesn't look like an inner function here, but it is, which is 2x. This is your answer. Now, we're going to have the logarithm functions. So log base b of x and then ln of x. So we're going to start with log base b of x. The derivative of it is going to be 1 over x times ln of the base. So if you have log base 3 of x, you're just going to get 1 over x ln 3. Now, as you can imagine, I mentioned ln x separately because it has a special property of ln of x. Well, what is ln of x? Ln of x is a fancy way of writing log base e of x. So, 1 over x ln of the base, which is e. Ln of e is 1. So the derivative of ln of x is just 1. Which is one of, if not the most important, relationships in all of calculus. And this works with the chain rule as well. if you have ln of 2x, that's going to be 1 over 2x times the derivative of 2x, which is 2. Now, what you may notice is that these 2's can basically cancel out. So it is 1 over x again. So the derivative, if you have ln of any really linear function, right? 2x, 3x, 0.1x, it's always going to be 1 over x. So we can write this even as the derivative of ln of ax is 1 over x. Next, we're going to look at sine of x and cosine of x. Not cosecant of x, cosine of x. So, these you just have to memorize. Derivative of sine of x, cosine of x. Derivative of cosine of x, negative sine of x. Alright, pretty simple. Again, works with the chain rule. So, if we, for instance, wanted to say sine of x squared, find the derivative. Well, cosine is our outside function once we take the derivative. So cosine of x squared times the derivative of the inner function, which is 2x. This is our final answer for sine of x squared. Now, derivative of tangent is not something that you specifically need to memorize. It's actually something that you derive. Tan of x is just sine of x over cosine of x. So this, think about it for a second, we could take the derivative of this. We know how to. This is the quotient rule. So we're just going to have the low function times the derivative of the high, so cosine x, minus high derivative of the low. So sine of x and then negative sine of x over cosine x squared. And I'm just going to write it like this. Now, this might not look like anything right now, but we can combine cosine x and cosine x into cosine squared x, right? This negative over here goes to here, so we get a plus. And then sine of x and sine of x, well, that's sine squared of x. And I can't erase it. But if you have sine squared of x, you, to derive it, have to know that cosine squared of x plus sine squared of x is 1. That's an identity. You don't need to know it for the tests because you can memorize this rule. But it's good to know in general. So you have 1 over cosine squared of x, which is the same thing as secant squared of x. So the derivative of tangent x is secant squared of x. And then from here, if you wanted to find secant, the derivative of secant x, that is 1 over cosine x, you can use the quotient rule. Same with cosecant, which is 1 over sine of x. Same with cotangent, which is 1 over tan of x, which is essentially cosine x over sine of x. Now, I'm just going to give you the answers to these because it's a lot of work to do quotient rule. So, derivative of secant is secant x tan x. Derivative of cosecant is negative, don't forget your negatives, cosecant x cotangent x. Derivative of cotangent x is negative cosecant squared of x. These you could derive, but it is better to just memorize them. And they very rarely come up on the test anyways. So we're going to do some practice with multiple chains. Because if you have sine of x, sine of ln of x squared plus 2, this can just be done by taking the chain rule over and over again. So with what we know now, how would you solve this? Well, you go from outside in. So first, the sine is going to transform, I'll start writing it from over here, is going to transform into cosine ln x squared plus 2. Okay, now we're going to move one layer inwards. Ln is going to be 1 over this, x squared plus 2. Now we're going to move one layer inwards to x squared plus 2, which is just going to be 2x. So your final answer is 2x cosine ln x squared plus 2 over x squared plus 2. So always, when you're doing multiple chains like this, always remember to go from the outside inwards. Don't try to skip any steps, because you can always mess something up if you skip steps. So writing it out is good. Writing out that like you're timesing this by timesing that by timesing that will help you reduce the amount of mistakes. And you'll always have at least one of those extended chain rule questions on the AP test. So right now, we're going to come back to the limit definition for a second. Now that we know what we know about e to the x, ln x, sine of x, all these different functions. If I told you that this was a constant, then how would you find it? Well, we know the limit definition of the derivative. If I gave you sine of x plus h minus sine of x over h, then you, in your brain, should be thinking, this is the derivative of sine. Now, since I added a pi over 3, you should first be thinking, this is the derivative of sine, and then you should be like, this is the derivative of sine at pi over 3. So what is the derivative of sine? Cosine of pi over 3, which is just going to be 1/2. Got to know your unit circle. So very often on the AP test, almost always, you will have some sort of limit definition of the derivative. Whether you get just a function and it asks you to find what this is, or more often, you will have some sort of constant of a function, like it will say sine pi over 3 plus h. And then that means find the derivative at that point, at pi over 3 in the last case. You have to keep that in mind always. Finally, we're going to talk about what is differentiability. Well, simply put, it is places where the derivative exists. So, if you have any function, let's say sine of x, you can write the derivative as cosine of x. Sine of x exists everywhere. Cosine of x exists everywhere. So these are differentiable on their entire domains. However, let's say I gave you a function like this. We're going back to limits here. This, sure, it's differentiable over here, but it's not over here because what's the derivative here? You don't know because it's not continuous. So, for a function to be differentiable at any point, it has to be continuous. Means continuity. So if you see that function f of x is differentiable across its whole domain, and you were doing a proof problem such as IVT, you could say, because it is differentiable, it is continuous. However, it does not go both ways. If you have, let's say, a function with a sharp turn, like here, or a function with a vertical tangent line. I tried my best to draw. This is not differential because how would it be? What is the derivative here? Is it 0? I mean, maybe, but it's not really, nothing's really happening there. It goes from sharply decreasing to sharply increasing instantly. There's no smooth kind of curve. Here, you can find the derivative. It's going to be infinity because it's a vertical tangent. The line goes straight up at that point. So even though there is a derivative, it is not differentiable because the derivative is infinity, which is essentially dne. So, differentiability means continuity, but continuity does not necessarily mean differentiability. Now, our final topic for the video is mean value theorem, or MVT. So, if we have, again, point B, and then point A, right? Now we're going to draw what's called a secant line. That was a terrible secant line. We're going to draw what's called a secant line between A and B. So this secant line is the average rate of change between these 2 points. Now, what MVT says is that on a differentiable interval between A and B, f of b minus f of a over b minus a must exist as the slope of at least 1 point in that interval. So, you see this line right here connecting A to B. You can see that at this point, and it looks like at this point, you have this secant line equaling the derivative. So at some point on any interval like this, it has to do that, as long as it is differentiable. Here's what can happen if it's not differentiable. You can have a function where A is here and B is here. The average rate of change between them, let's say, is 0, right? Then you can have a linear line, and then a hole, and then a closed hole, and then a linear line. Now, the slope on this curve is at no point 0. This cannot satisfy MVT because it is not continuous and therefore not differentiable. Now, how would you write this out formally? Well, you would say, since f of x is differentiable then or you should say, because it's differentiable on a b, on the interval a to b. This part is important because without that, you get the whole thing wrong. There must be a c where a is less than c, which is less than b, so c is between a and b, the interval, where f prime of c equals f of b minus f of a over b minus a. So, it's differentiable on a, b, and between a and b, there's at least some point where the derivative will equal the average rate of change. This is essentially MVT. If you write it out like this, then this will be a full credit response. And that is basically it for this unit. So the main takeaways. Remember limit definition of the derivative, because they will have a question like this on the test. 100% guaranteed a limit definition of the derivative on the test. Keep in mind all of the rules. Power rule, product rule, quotient rule, chain rule. They're very useful, and they 100% come up as well. All the time, you need to know them. Main derivatives to keep in mind, you don't need to know all of the ones I mentioned, but e to the x, ln of x, and then sine of x and cosine of x come up quite often. You will almost guaranteed see all 4 of these on a test. You might also rarely see an a to the x or a log base b of x or a cotangent of x, but they're very rare. And then know that differentiability equals continuity, because this comes up heavily in later units. And, of course, remember mean value theorem. It's a theorem that will show up on the test at least once. You just need to know it. All of the theorems will show up on the test at least once. And that is it for this unit. Thanks for watching.